Okay. Hello everyone. So today we'll go over the sample problems for the junior division of JPOMO. So the sample problems this time, as with the actual contest, have a bit of a different structure. So today there will only be four short answer problems, and this time there will also be two proof problems. But don't worry about the proof problems. We will go over them with a bit of a slow pace. Okay, so let's start with this first problem. This is a bit of a warm-up. For those who don't know about number bases, I'll just do a short intro first. The When we have a number written in base in another base other than 10, let's say 1, 2, 3 base 4, that's essentially a shorthand for this. So 1 times 4 squared plus 2 times 4 to the first, and then 3 times 4 to the 0. And so these are kind of like the digits in a number that is expressed in another base. So that is kind of just a notation. You can think of it that way. And so with that, here's the first question. So find the number of positive integers x from 3 to 999 inclusive, such that 12 written in base x times 12 written in base x plus 1 is equal to 110 written in base x plus 2. I'll let you guys think about it first for maybe 2 minutes. Essentially, number bases are just writing numbers in another way. And base 10 is just the normal way in which we write numbers. So yeah. So so by the way, we highly encourage that you guys participate in giving ideas or maybe even answers so that the discussion will go through faster. So I'll let you guys think about this first for a moment. Yeah, okay. So what would you guys do as a first step into solving the problem, given that what- given what I showed earlier, which is that bases are basically just notation. So how would we approach this first? Okay. So one sent a solution. Okay, yeah, that is correct. Uh, okay. For the others, what do you think is a good way to start uh, approaching this problem? Uh, yeah, okay. So firstly, we would like to write hold on. So we would like to write this equation here in a way that we could better understand because looking at it with basis is a bit complicated. It makes it look a bit complicated. So let's write it in a simpler way. So first, let's deal with the 12 base x. We can write that as 1 times x to the first plus 2. Note that I'm being a bit verbose here, um, just so that you guys get the idea of how this is going. And then the second number is 12 base x plus 1. So that's 1 times x plus 1 plus 2, which is equal to 110 base x plus 2. So that is 1 times x plus 2 squared plus 1 times x plus 2 plus 0. And then we can simplify this, right? So this is x plus 2 times x plus 3 equals, uh, I'll, I'll just spare you guys of the simplification. The right-hand side will just become x squared plus 5x plus 6. And notice that if you expand the left-hand side, no, it will become it will also become x squared plus 5x plus 6 equals x squared plus 5x plus 6. So do we notice anything from here? The answer at this point should be very obvious, kind of. So notice that both sides of the equation are the same. So it basically means that um all values of x will satisfy the equation. And that means that all positive integers, x from 3 to 999, will satisfy it. Therefore, the answer is basically the number of integers from 3 to 999, which is 999 minus 3 plus 1, or 997. The plus 1 here is just so that we can basically include the sliding number in our count. Questions so far? So again, I would like to highly encourage everyone to actively participate, so that the the discussion will go faster and is also more enriching in a sense. Yeah, all X works. Uh, you can kind of easily modify the equation to make only some X work. Yeah, if we have no other questions, let's move on to the next one, which is kind of more complicated. So this one is algebra this time. Okay. So let alpha, beta, and gamma. Oh, yeah. Usually I don't wear glasses. So Let alpha, beta, and gamma be the roots of the cubic equation x cubed minus 7x squared plus 3x plus 2 equals 0. If the cubic equation x cubed plus px squared plus qx plus r equals 0 for some integers p, q, and r has the roots alpha plus beta, alpha plus gamma, and beta plus gamma, find p plus q plus r. Yeah, this has something to do with Vietas. So I'll just give you guys a starter also. Um, this problem is actually pretty nice in terms of getting the values. I'll show that in a while. To give you guys a starter, the sum for those who know Vietas, what is the sum of the roots here of the original equation? So what is alpha plus beta plus gamma? Yeah, it's 7. So essentially we just get it from here and then negate the coefficient, right? So this is 7. Alpha, then what is alpha beta plus beta gamma plus gamma alpha? So it's 3. And then lastly, alpha beta gamma here is -2. So I'll just give like a brief introduction for those who don't know how where these came from. So the 7, the 3, and the 2 came from these coefficients. So notice that since the cubic is monic, we can simply get the coefficients. However, the signs alternate between negative and positive. So, for example, for the first one, we have to negate this. We have to negate the -7, so that it becomes +7, and then the second one we don't have to negate it, and then the last one we do. And notice that the expressions we get here are have degree 1, degree 2, and degree 3. So basically, this just the sum of the sum of the roots, then the pairwise products, then the product of all three. So if we have higher dimensions, it will just be product of one root, product of two roots, product of three roots, and so on. So I'll let you guys think first about the actual question for maybe for a few minutes. Yeah. Uh, so basically, the what we're looking for using the same technique kind of is the following. So P is just the negative of the sum of the three new roots. So that's just alpha plus plus beta plus gamma plus alpha. And so if you simplify this, this is already pretty straightforward. So this is -2 times alpha plus beta plus gamma. So what is the value of P for this one? Let's see. So from here, we get that the value of P is -2 times 7 equals -14. So essentially, we just substituted this one that we already have. Okay. Now let's go for Q, which is slightly more complicated. So this time, since this is the second sum, we don't have to negate. And so this is just the sum of the pairwise products. By pairwise products, by the way, we mean the products of of any two of the roots. So in this case, that would be alpha plus beta times beta plus gamma plus beta plus gamma times gamma plus alpha. And then lastly, uh, yeah, then gamma plus alpha and alpha plus beta. So notice that if you expand the first product, you should already see something coming. Um, if I expand this one, then I get, I'll do this by FOIL. This is alpha beta plus alpha gamma plus beta squared plus beta gamma. And I'll give you guys a tip. Uh, Notice that the entire expression is symmetric. So basically, if I expand the first product, I already know that the other two products will look like this. And that can already tell me what the entire thing looks like. And so I can say that since there's a beta squared here, I also know that there's a gamma squared and there's an alpha squared. So I can already write the first part of the expression as alpha squared plus beta squared plus gamma squared. And then now we account for the other three terms. If you expand the other two products, there's also you will also see these terms appearing. So that is 3. So the entire thing is just 3 times alpha beta plus beta gamma plus gamma alpha. There's a question here. How do I tell if it's symmetric? Basically, the definition of symmetric is if you switch any two of the variables, then the expression should still be the same. So for example, here, if I switch alpha and beta, then this then the expression will become beta plus alpha, then alpha plus gamma, and then plus alpha plus gamma, gamma plus beta, and then lastly, um, hold on. And then, but you get the idea. Um, Essentially, if you do that, then the expression should still be the same. If you work with enough symmetric polynomials, then you could then at some point you can get this feeling that something looks symmetric just by looking at it. Hold on. Yeah, so what Philip and Ethan Choi said also. Yeah. Okay. Now, if we look at this expression, we're still not completely done because we have alpha squared plus beta squared plus gamma squared, which is not that straightforward to find. And so, um, what we do is, yeah, use the square of a trinomial. So what we do is we rewrite this as alpha squared plus beta squared plus gamma squared plus 2 times alpha beta plus beta gamma plus gamma alpha plus this thing again, right? And notice that these terms form the square of the sum of the three. So that's alpha plus beta plus gamma squared. And then we add in the final hold on, plus alpha beta plus beta gamma plus gamma alpha. Okay, and then evaluating this is pretty straightforward now. So that's 7 squared uh, plus 3, which is 52. I'll zoom out a bit. Okay. Lastly, we go to R. Okay. Um, so R in this case is the product of all three of the new roots. So this is alpha plus beta times beta plus gamma times gamma plus alpha. Okay. Notice that actually an easy way to evaluate this is to notice that we can rewrite alpha plus beta as 7 minus gamma. Why is that? You can get it from here. Just subtract gamma from both sides, right? And so using this, we can rewrite this entire expression in a way that's more manageable for us. So that is 7 minus gamma, 7 minus beta, 7 minus alpha. Okay. And expanding this, I'll just spare the expansion for you guys. 343 um, minus 7 squared, 49 times alpha plus beta plus gamma. Okay. Plus 7 times alpha beta plus beta gamma plus gamma alpha minus alpha beta gamma. You probably noticed that if we substitute this one here, then this entire thing cancels. So we can also get an identity here that this one is actually equal to alpha plus beta plus gamma times alpha beta plus beta gamma plus gamma alpha minus alpha beta gamma. So just something worth noting. But I wouldn't really recommend memorizing it also because deriving it is pretty easy if you know this transformation. So yeah. If we substitute everything here, this is 343 minus 49 times 7. As I said, this will cancel out. And then plus 7 times 3. Then minus negative 2. So this is 23. Okay, cool. And therefore, since we're asked for P plus Q plus R, oh wait, hold on. Oh, R should be negative of this. So just negative everything, right? So R is actually negative 23. So remember when doing betas, always be careful about the signs. And therefore, we get that P plus Q plus R equals negative 14 plus 52 minus 23, right? And you should get that the answer is 15. Any questions or anything? Comments? I just saw the solution that's here. Eventually, the your Q should be 7 squared plus 3 because it's plus 3 times AB plus AC plus BC. Yeah. Do you have any questions or anything? Okay. If there's none, I'll move on to the next question. Um, yeah, I apologize in advance if I mispronounce any of the following names. So this is a combinatorics expression from paper D. You may notice that a lot of the sample questions for today are taken from the qualifying stage, also so that we can review some of the questions we had given. Okay, so this is combinatorics question. So the 12 crystals airs of Alpharius are seated around a round table. So I'll draw that round table now. Note that since this is a round table, um, rotations are considered the same. So if I rotate the table, then that would still count as one arrangement. And all airs are distinct. Due to internal conflicts, the following conditions must be satisfied. Anaxa and Aglaia must sit directly opposite each other. Hyacinth must sit adjacent to Aglaia, and Final and Maide must not sit next to each other. Let n be the total number of distinct seating arrangements that satisfy these conditions. Find the remainder when n is divided by 1000, or in other words, find the last three digits of n. So first I'll draw this round table so we have a visual. So I'll give you guys maybe a few minutes to think about the question. Okay. Uh, Seems that there is nothing in the chat so far. Anyway, let's go over the question. So again, as I said, rotations are considered the same. So basically, so that we don't have to deal with over 12 anymore, let's fix one of the people already in their seats. So for brevity, I'll just number the people. So this is 1, 2, 3, 2 again, 4 and 5. So in the diagram, I'll just refer to them by their number. So notice that we can fix one, then the seat of two is already determined. So number two is seated directly opposite already, right? Then then three has two options on where they could seat. So either here or here. So we already have a factor of two in our in our expression for for n. Okay. So it's n equals two times something. Okay. Then there's one more condition which we haven't treated yet, which is these two must not sit next to each other. What I'll do here is kind of complementary counting. So let me start by asking a question. So let's assume for now that three is seated here. So basically, these four seats and these five seats are not yet occupied. So what is the total number of ways that the two the two others can choose their seats? Yes, just them. We're gonna do like a complementary counting approach here. Not 9 factorial since there are just two people. 9 factorial is basically like the number of ways to arrange everyone else. Okay. Uh yeah, so it's 9 times 8. Basically because yeah, this is the intended solution actually. The 9 is basically the number of ways that the first person will choose, and then 8 is for the second person. And so we have 9 times 8 here. Now we wish to remove the people who no. We wish to remove the cases where the two of them sit together. So how many ways are there for them to sit together? Yeah, so 14. Note that there are 7 possible pairs of seats that they could occupy. So it's these 3 on the left and these 4 on the right. Okay. And there are 2 ways for them to occupy the seats. So if one is on the left and one is on the right and vice versa. So 9 times 8 minus 7 times 2 for the two of them. Basically, the 9 times 8 minus 7 times 2 is the number of ways that they can occupy the seats such that they don't sit together. And lastly, we have the other 7 people, who have no restrictions, so we just put 7 factorial, since that's the number of ways that we can arrange them. Yeah. I'll spare you guys the calculation. The last 3 digits here should amount to 640. which is the final answer. Note that during contests, I would also recommend that you kind of know at the back of your head the first few factorials. So for example, I immediately know that 7 factorial is 540, 5040. And so calculation is kind of faster. But of course, if you still have time, you can just derive it to make sure. Do you have any questions or anything? Okay. If there are none, let's move on to the next question. After this question, we'll just have a few minutes break before we move on to the last two. So yeah, this one is geometry this time. When trapezoid ABCD with AB parallel to CD, just draw the diagram. We have that BD and AC are diagonals, so essentially these two that go across the quadrilateral in some sense. So I'll label the points as hold on. Yeah. A, B, C, and D. It says here that AC is perpendicular to both AC and BD. And if angle B is 45 degrees and angle D is 30 degrees, then basically find this. The answer extraction shouldn't be that necessary. Yeah, I'll give you guys a few minutes to think about it. Actually, this geometry problem shouldn't be that hard. Uh, yeah. Okay. Yeah. So there is already something here. Um, so first it would be good to assign a variable since there's no given lengths here and we're asked for a ratio. So first I'll let AC be x, and then we'll express everything else in terms of x. So this is x. Since angle B is 45 degrees, uh, what is AB? Yeah, AB is also x. The reason for this is that triangle ABC is a 45, 45, 90 triangle. And and from there we can see that AB equals AC, and so it's also x. Now, um, what is CD in terms of x? Yeah, so it's x square root of 3. So since angle D is 30 degrees, we can see that triangle ACD is a 30, 60, 90 triangle, and so CD is x square root of 3. Now we want to get BD. So what is a good approach that we can use to get the length of BD? Yeah, you can move CD down uh, to BA. So if you want to rigorize this, you can say something like extend BA and the line that is perpendicular to CD. So essentially, in other words, drop an altitude from CD to line AB. So essentially, we have this. And why is this useful? We basically have a right triangle over here, right? I'll name this point P. And since CD is x root 3, we have that AP is also x root 3. And now, what is BD in terms of x? This is essentially the final answer if you think of it. Okay, there's nothing in the chat. Ah, there. So let's go through this. So since we have AP equals x root 3, we have that the entirety of BP is equal to x plus x root 3, but I'll factor out the x and just write 1 plus root 3. X, okay. And since we have the right triangle, BPD, we can get that BD squared. I'll just write BD squared so that we don't have too much issues. That is BP squared plus DP squared by Pythagoras. So that is 1 plus root 3 x squared plus x squared. I'll spare you guys of the simplification. That is 4 plus 2 root 3. Wait, yeah, yeah, 4 plus 2 root 3 x squared plus x squared, or 5 plus, wait, theta ba? Okay, there. That is 5 plus 2 root 3 x squared. And therefore, BD over 8, the square of BD over AC is 5 plus 2 root 3 is essentially BD squared over AC squared. So that's just 5 plus 2 root 3 times x squared over x squared, or 5 plus 2 root 3. And the answer extraction gives the answer as 325. because it was asking for 100 times this plus 10 times this plus this one. Questions? Okay. If we have no questions, we'll have an around 5 minutes break. Please be back by 8 p.m. Okay. Before we go to the last two problems, uh, we'll just go over basically a short intro to solution writing. So the as you may notice, the JPOMO finals includes two questions that will require you to write full solutions. And we at JPOMO believe that uh, introducing solution writing early is important because, for one, communicating your ideas is an important skill in a lot of areas in life, and number two, um, you will encounter proofs and solution writing in general as you go to higher level contests or basically higher math in general. So yeah, let's go through this. Before I show what we would expect from a solution, I'm going to ask you guys this first. Say you were given two proofs that that of the statement, the sum of two even integers is even. Which of these solutions would you rather read and why? So these are the two solutions. The the more important question actually here's the why, because I want to see what you guys think are ideal standards of what a good solution looks like. I'll just wait a few minutes. It would also be helpful if you guys state why you would rather read one. Um, because I want to see what you guys think are what you guys think are ideal of characteristics of a good solution. So I'll give maybe 1 more minute. Okay. Um, it seems that we kind of have a unified answer here. So basically everyone prefers to read chubby solution more. Um, I'll point out some obvious flaws with Penrick's solution. Firstly, it's not that legible. If you may notice, there are also a lot of um, erasure marks somewhere, and there's also like a lot of wrong spelling, like number and because and things like that. And it's not that organized in the first place, compared to Chubby solution, which is very organized. And yeah, so firstly, I want you guys to keep in mind that when you write solutions, someone else is going to read your work. Um, Especially that is a contest. Since you are writing solutions as a submission for a contest, it is usually fine to write just enough so that the grader can understand your work. So your goal in writing the solutions, at least for this contest, is to convince us that you know how to solve the problem fully. And by solving the problem fully, I'll talk a bit more about that later on. So first, I'll state the obvious. Be very clear with what you're trying to do. So of course, write legibly. And we would also prefer that you guys write in sentences because if you just write equations, then it's kind of easy to get lost with the crazy amount of symbols that's there. So we would prefer that you guys write in sentences so that the flow of the proof is also natural in a sense. However, if you are running out of time, then it would be okay to not write a few parts in sentences, um, especially in equations. What I would like to do uh, is to just put some implications using the imply symbol. Hold on. Is to just use the imply symbol, the one that looks like the following. This one. Or something like that. So essentially you have a statement here, then another statement here. So if you don't really have that much time, you can just do that. That would also be fine, but as much as possible, please write in sentences because that writing in sentences is the best way to um, explain your ideas. And please clearly define any new variables or terms that you'll use in your solution. So for example, don't be too vague. The best possible way to define it is to be as specific as possible so that A and B be even integers is better than let A and B be two numbers. Or but if you just want A and B to be two real numbers, then that would be fine. But it would also be better if you specify that A and B are two real numbers instead of just numbers. And the worst possible case is to completely omit this because in your solution, if you pull out A and B without stating what they are, then how would we possibly know what those are? Okay. So as you can see, Chubby did that very well. He stated here that A and B be even integers, and then proceeded with a proof based on that. And you should also explain your reasoning well. Note that if we ask you to prove or show that a statement is true, then you should give basically a full explanation on why the statement is true. It is not giving examples that support the statement. So, for example, this is also why Penchick's proof is wrong, and it's not even counted as a proof. So he just wrote the examples here, 2 plus 2 equals 4, 2 plus 4 equals 6, and so on. But this is not a proof. Why? Because what about the other possibilities? He didn't consider like the quote unquote proof here doesn't consider the case of, let's say, 62 plus 64. Is it also even? And things like that. However, if the question asks you to prove that something exists, then it's fine if you just give some examples, as long as you show that the examples indeed satisfy the conditions. So, for example, if we have a problem here, prove that there is a natural number that is divisible by both 2 and 3. Obviously, you can think of one at the top of your head already. Um, this would already count as a complete proof. So first, you could state the said example, we claim that the number 12 is a natural number divisible by both 2 and 3, and then state why it satisfies the condition. So since 12 over 2 is 6 and 12 over 3 is 4, and these are both integers, we conclude that then you just state the conclusion again. And of course, proofs for actual problems will likely be much longer than this. Oh, also, please write correct math. One small mistake um, can entirely trip up your entire solution. If you still have remaining time in the contest, it is always worth it, and I highly recommend that you go through your solution and check if you have any typos or logic gaps or anything, um, and that everything you wrote is completely correct. So I saw that this has already been mentioned in the chat, but Penchick also fell for this and put 8 plus 8 equals 67, which is obviously wrong. And note that since 67 is odd, it doesn't even satisfy the condition. And so that would already disrupt his entire proof, even though it is not even a proof. So with this if this were true, then what is being asked is not true in the first place. And an even more common mistake is writing the proof backwards. What do I mean by that? The proof goes from what is being asked to something that we know is true. You should not do that because if A then B doesn't always mean if B then A. And these statements are called converses of each other. An easy example of this is we know that all squares are rectangles, but not all rectangles are squares. Yeah. So for example, we have this problem. Prove that for positive numbers a and b, we have a plus b over 2 is always greater than or equal to the square root of ab. Some of you may recognize this as the two-variable version of the AMGM inequality. I'll show first the wrong proof. So notice that it starts with multiplying both sides by 2 gives this. Notice that this one comes from here. Another way to think about this is, why are you using the statement here when you don't know that it's true? So essentially, this entire proof is wrong. Something like that. The correct proof is the version of this that is written in the other direction, which is this. It starts with something that we know is true and then builds up from there and ultimately ends up with what is being asked. So since the square of any number is non-negative, we have this, and then after some line of reasoning gets to this one. Yeah. And some other types of problems. Yeah. If the problem asks you to find all objects that satisfy a certain property, you must first state what these objects are. Then second, show that they satisfy the property. Please remember not to leave this out because it is still an important part of the solution, even though it might be very easy. And third, show that there are no other objects that satisfy the property. Similarly, if the problem asks you to find a minimum or maximum value of something, then first state the answer. Second, show that this value is attainable. Note that if it's not attainable, then it isn't even a possible value of the quantity. Then third, show that there cannot be a value lower than if asked for a minimum or higher than if asked for a maximum, your answer. So essentially show that what you have is indeed a minimum or maximum. If you forget these points, don't worry. The proof questions in the actual contest will include these as a guide. For more comprehensive tips, you can check out this handout, which is also linked in the sample problems as a resource. And additionally, the sample problems document has a handout version of this presentation that you can also check out for your own reference. Okay. Any questions or anything? Okay. Um, just a heads up. It is 8:14, so we might be kind of over time also. And but we'll still go over the two proof problems with a reasonable pace. Questions or anything? Oh yeah. Pasted in the chat also are all the pointers that I mentioned earlier. So you can check those out as well. If there are no more questions, now I will go over two proof problems from the sample problems. That will also show us how we can think of proof problems and then write them up later. Okay. So the first one is geometry. Uh, and it reads as follows: let ABC be a triangle, and let D be an arbitrary point on the perpendicular bisector of BC. So essentially this line here. Suppose that the internal angle bisectors of angle ADB and angle ADC intersect AB and AC at x and y, respectively. Show that XY is parallel to BC. So to start, I'll just mark the angles here. So these two angles are congruent. And also, these two angles, okay, hold on. These two angles are also congruent due to the angle bisectors. So our goal here is to show that XY is parallel to BC. I'll let you guys think about this first for a few minutes. Okay, so I'll start going over this problem now. Notice that we have some angle bisectors here. So one thing that we can do is to try the angle bisector theorem. Now, what is the angle bisector theorem? Suppose we have a triangle here and an angle bisector here. Then I'll name these as A, B, C, and D. Then A over C is always equal to B over D. This is called the angle bisector theorem. And you can cite this in your proof without explaining basically the proof of the theorem. There. So we can use this on two triangles. Okay. Um, what triangles do you guys think we should use this theorem on? ADX and BDX. Actually, let's just refer to the whole triangle. So ADB, this one. Hold on. ADB here. And what's the other triangle? Notice that we have two angle bisectors here. Yes, ADC as well. This one, right? So notice that if we do the angle bisector theorem on triangle ADB, then we have that DA over AX is equal to DB over BX. And from triangle DAC, we also have that hold on, dA over AY is equal to dC over CY. Okay, and another thing, note that we're asked to show that XY is parallel to BC. And I'll just erase this. And this configuration here with XY and BC should look a bit familiar to some people here. So what do you think can we prove to ultimately show that XY is parallel to BC concerning triangles AXY and ABC? Yeah. So essentially, another way to state this is uh, we we want to show uh, that triangle AXY is similar to triangle ABC. Okay, and that could ultimately give us these two equal angles, and we can get the parallel from there, right? And a good thing to aim for is to show that AX over AB, actually AB over AX equals AC over AY. Right? So essentially, we already have two ratios here that already have all of those lengths. And we would what we would want to do is we would just want to manipulate these ratios. So I'll just name this one and two. Okay. And so if we want to manipulate ratio one, we want to somehow get an expression for AB over AX. What I'll do first is I'll rewrite it as follows. So one implies this Bx over Ax equals dB over dA. Okay. And to get AB over AX, that is just 1 plus this ratio, right? Because AB equals AX plus AX plus BX, right? So hold on. Yeah. And so we get that AB over AX equals 1 plus B. Actually, I'll just write the entire thing out. This is just AX plus BX over AX, or 1 plus BX over AX equals 1 plus the dB over dA. And then for 2, we can do the same thing also. This time we want AC over AY. I'll not write everything out anymore. If you're doing the same thing for two things, you can also say like similarly, this is also true for two or something like that. Uh, yeah. So AC over AY equals A AY plus CY over AY equals 1 plus CY over AY. And that's the same as 1 plus oh no. Yeah, 1 plus DC over DA. Wait, hold on. Yeah, and self-similarly, you can also do analogously. That would also work. If now we want to find a way to link these two, right? These two expressions, so that we can ultimately say that AB over AX and AC over AY are equal. Uh, our, the way to do this is to notice, you can also check from the diagram that DB indeed equals DC, right? Um, a well-known fact is that since this is the perpendicular bisector of BC, okay, we immediately know that DB equals DC. So since DB equals DC, we have, I won't write everything out anymore. Vx over Ax equals AC over AY. Okay. So essentially we have the proportion that we want already. Then we just want to show the similarity. So we're going after SAS here. So we also want to show the angle, since angle BAC equals angle uh, XAY. We have triangle BAC. I'll just write ABC. Um, Triangle ABC is similar to triangle AXY, pardon the handwriting, um, by SAS similarity. And therefore, this is the therefore symbol over here. Um, Therefore, we have angle AXY equals angle ABC. And so XY is parallel to BC, which is what we wanted to show. Any questions? I'll show an example of fully written proof for this question. You guys might want to take a screenshot, but it will also be uploaded in the sample problems document maybe later or tomorrow. So here, notice that here we wrote everything up, kind of. So like, for example, here, since AB equals AX plus BX and AC equals AY plus CY, then we have this. But note that instead, I wrote this entire thing as just one equality. So it's just a chain here, right? Then we have this, and then therefore, yeah. So generally, a well-written proof will look something like this. If there are no more questions, let's move on to the last one. I apologize as we're going over time, but let's just finish this a bit quickly. This one is from paper C, but I modified it so that it's asking for all positive integers that appear in all three sequences. So Pelican, Chubby, and Renren each list arithmetic sequence. Pelican sequence begins with 4, 11, 18. Chubby sequence begins with 13, 28, 43. And Renren sequence begins with 6, 25, 44. Determine with proof all positive integers that appear in all three sequences. So since we don't have much time, I'll dive right into the solution. A good first step to do is to write down formulas for all of these sequences. So I would like you guys to give a formula for each of the three sequences. Yes, formula for the nth term of each sequence. Or just give me one at least. Okay, there is something on the chat. Yes, that is correct indeed. So anyway, I'll just give the formulas nonetheless since we don't have much time. I'll write all yeah, I'll write all of the formulas in terms of n minus one because the how I want you guys to think of the problem arises from there. So this is 7 times n minus 1 plus 4, as shown in chat. The second one is 15 times n minus 1 plus 13. And the third one is 19 times n minus 1 plus 6. Notice that if we think of it this way, then it's clear that if there is a positive integer n that appears in all three sequences, then it will satisfy the following properties. So n has a remainder of 4 when divided by 7, 13 when divided by 15, and 6 when divided by 19. Essentially, what all of this means is, what I'm writing down basically is the number here is the remainder, and the number here is the divisor. So I can read this as, for example, n is congruent to 4 modulo 7, or n is 4 mod 7 for short. Okay, and from the first one, I can write n as 7k plus 4 for some positive integer k. Well, non-negative integer k, rather. And so we can substitute this in the second congruence. By the way, you call these ones congruences, not equations, because they don't use the equal sign, rather it's they use modulo. So yeah. If we substitute this in the second congruence, we have 7k plus 4 congruent to 13 mod 15, or 7k congruent to 9 mod 15. To solve a congruence of this type, essentially just try to think of a number that when you multiply a number between 0 and 14 inclusive, such that when you multiply it by 7, it has a remainder of 9 when divided by 15. So I'll save the trial and error for you guys. This would result in k is congruent to 12 mod 15. Okay, and that means that we can write k as 15m plus 12 for some non-negative integer m. Okay, and therefore we can substitute this in n. That will give us that n is 7 times 15, 15m plus 12 plus 4, which is 105m plus 88. And then we just essentially do the same thing again. We substitute this into the third equation, third congruence rather. This one would give 105m plus 88 is congruent to 6 mod 19, or 105m is congruent to negative 82 modulo 19. Notice that these numbers are not within the range of 0 to 18. And so we would like to simplify this further. 105 is 10 mod 19, and negative 82. Negative 82, you can treat it as equivalent to positive 13, I think. Yeah, positive 13 modulo 19. Notice that negative 82 is 13 more than negative 95, which is a multiple of 19. So that's one way to think about negative numbers here. And I'll spare you guys the trial and error again. Hold on. Yeah. M is congruent to, if I remember, yeah, 7 mod 19. And therefore, we can write M as 19L plus 7. And we can substitute that here. So 105, 19L plus 7. Pardon the handwriting again, plus 88. And then after calculating, you should get that this is 1995 L plus 823. Therefore, all numbers of this form for L non-negative integer satisfy the condition and thus appear in all three sequences. So note that we just solved a system of what we call a system of linear congruences. And note that all the moduli here, we call these moduli, are relatively prime. The fact that such thing would produce a unique solution, modulo some number, is called the Chinese remainder theorem. You'll hear this a lot in some number theory problems. So just introducing it in. So again, I will show a fully written solution to this problem. Just put it here. You guys can also screenshot this if you want, but this will be up at the POMO website soon. So notice that in solving this problem, I would recommend that um, you first think about it, try to solve the problem before writing the proof. But if you have no time, you can also write the proof already. So notice that this proof follows the format that I stated earlier for find all problems. So first state the answer, then show that all such integers satisfy the condition, which is this. Notice that I also included the three conditions here. And then after that, uh, show that those are the only solutions. This would work as a proof already because we went from the three conditions to n is of that form. Okay. And one more note, I used this notation here, n union 0. That just means the whole numbers or 0, 1, 2, 3, 4, and so on. Okay, cool. Do we have any other questions? Yeah, you could just use the W symbol, but I don't see that a lot in math documents. Like the the more used notation other than W is for one, this one, and also yeah, there's also a debate on whether whole numbers include zero. I think there's also a debate on whether natural numbers include zero or not. So I also see people use the notation z greater than or equal to zero. So yeah. And also if you just put W, then not all the graders may understand what W is. So you could also, so if you don't want to use W, you can use this one or this one. So the z greater than or equal to zero just means integers greater than or equal to zero. Yeah. Hold on a bit. Just some announcements before we end. I'll show the announcements real quick. I apologize for being a bit over time. There were also some delays that happened earlier. So yeah. Here are some a couple reminders before we end. The recording of this lecture, if you want to go back to any part of it, will be available on our YouTube channel shortly, which is linked here. For those joining the JPOMO final stage, which is probably most of the people here or everyone here, Please be sure to read the contest primer, which can be found at the same link as the primer for the qualifying stage. Note that there will be no additional registration steps in the POMO website, and registration has been closed and was due last Friday. The next lecture for the primary division, if you or anyone you know will attend, is tomorrow at same time, 7 p.m. So that is it for today. Thank you for coming to the lecture. We hope that this helps in your preparation for JPOMO. Yes, same link for tomorrow. Thank you, everyone.